This lesson has a hodgepodge of topics in it. All these topics are kind of easy, so they're just thrown together when we're talking about graph characteristics. We're going to talk about multiplicity of zeros, number of turns, local minimums, local maximums. Okay, a polynomial. Look at this graph right here. It's in red, and I extended it on down in blue so that you knew that the graph keeps going this way and keeps going that way. All right. When we're talking about the degree of the polynomial, we're talking about the highest exponent that it could have. That's the degree, the highest exponent in the thing. All right, now, the reason this says that a polynomial of degree n will have at most n minus 1 turning points is because some of these things could have a zero that's a multiplicity, which we'll talk about that later. So it could be a degree that's higher than what we say. But at least this is the lowest possible degree that this will have with this many turning points. So your turning points are honestly your hills and your valleys, and you just count them. So this is 1, 2, 3. So I have 3 turning points, and remember, turning points is smaller than degree. So even though the way this is worded, even though it says that it has n minus 1 turning points, that's kind of confusing. N minus 1 is 3, so the number is 4, because 4 minus 1 is 4. So your degree is bigger than the number of turns. It's 1 bigger. So this graph has a degree of 4. Okay, this one, we want to count again the turning points. 1, 2, 3, 4, 5. So this has a degree of 6. All right. Now, sometimes they don't give you the graph and they give you n. Remember that n is the degree and n is larger than the number of turns. So if n is 4, 4 minus 1 is 3. If n is 7, 7 minus 1 is 6 turning points in the graph. We want to determine the x-intercepts. Remember, the x-intercepts are the solutions. It's where this is set equal to 0. So if I take the function and I set it equal to 0 and I solve each one of these, x minus 1, add 1 to both sides, x is 1. Subtract 2 from both sides, x is negative 2. Add 4 to both sides, x is 4. So my zeros, the x-intercepts are at 1, negative 2, and 4. But it's also the zeros of the function. All right. So looking at this one, and remember, it's just the opposite. So it's like in elementary school, you saw blank minus 1 equals 0, and you wrote 1. You can honestly just do that in your head if you think about it. You don't have to write out all those steps. So this is negative 3, this is 1, this is negative 5. All right, I put this example in here in your notes because sometimes there's a variable on the outside of all the parentheses. So it's easy to do this one. This is just negative 2, 3, negative 5. And remember, you're setting them equal to 0. So if I take x and set it equal to 0, well, one of my answers is 0 as well. So if there's anything out here without a plus minus, it's just 0. Determining the multiplicity of each zeros. Now, sometimes your polynomial has a factor that's the same, like this one. That means that you're going to have a 0 at negative 3, but it's going to happen 3 times. So you're in the graph at negative 3. At negative 3, it'll kind of flatten out depending on which way it's coming. This one is probably coming from up here this way. Yeah, it's coming up here this way, and it'll flatten out a little bit at that instead of just being right on it. It'll flatten just a little bit, the curve will. All right, so that's what a multiplicity does. So you have one value of 2, you have 3 values of negative 3, and 2 values of 7. And you can recognize it by the exponent. So that's what multiplicity is. All right, identify, and in all honesty, these hills and valleys and this here, the multiplicity of the zero, it would become a little more apparent. There's a lesson coming later on. I can't remember now which unit it's in. I want to say it's maybe a couple units from here where I go into detail about what the graphs look like. And so this will crop back up. All right, a local maximum and a minimum. The local maximums are your hills and the local minimums are your valleys. So right here, that's a hill in the graph. You just name that point. It's -3, 5. This one here is a dip in the graph. You just name that point. It's 0, 0. That's your local minimum. Now, why am I calling it a local maximum and a local minimum? That's because if you extend this graph on down, it goes below that point. If you extend this graph on up, it goes above that point. So they're local. They're not absolute. An absolute minimum looks more like, let's see if I've got one in here. I do not. Okay. An absolute, I'm just going to temporarily erase this. It won't stay that way. An absolute minimum is like this. There is no point on the graph below that. That's an absolute minimum. On this one, there's no point on the graph above that. That's an absolute maximum.